Okay, so good afternoon. So I said I'm honored to be invited for this presentation today. And when Isabelle invited me, I gave a very general title, Are Soils Climate Smart? Because I intended somehow to speak about carbon sequestration in soils, but didn't know yet which direction. So it's a wide title, and I will address some facts, established facts, some ongoing processes and questions being studied, and some research needs. Nothing systematic, nothing comprehensive. Examples. Yes, how does it work? It works like that. So first, what are climate smart? What does it mean? It was actually defined by FAO for agriculture, that climate smart agriculture was an agriculture that was still productive under climate change, that was able to adapt to climate change, and that was able to contribute to mitigate climate change. And in a quite well-known paper, Keith Postian and collaborators restricted this meaning to contribution to climate change mitigation. The true definition is the wide one. I will today more focus on contribution to climate change mitigation, especially via carbon sequestration in soils. And if we go to numbers, facts, things that has long been well established, that soils are a major contributor to carbon stocks and fluxes globally. You see that there is twice as much carbon in the first meter of the soil compared to the atmosphere, and that it contributes to the fluxes from the towards and from the continental surfaces. This comes from this year publication of the Global Carbon Budget. It's a yearly publication, and I went back to their issues to see how numbers had changed about carbon. And I saw that numbers regarding the stocks have not changed. Very stable since the 90s, but since the 90s, the effluxes from deforestation, fires, changes in land uses have decreased. It was 1.4, it's 1.1. Explanation is, of course, there are methodological changes since then, but explanations are rather a decrease in deforestation. And you see the net sink from the atmosphere in continental ecosystems has increased, and this is explained by CO2 fertilization, nitrogen deposition, and also land abandonment leading to reforestation. So some changes in the numbers. Now, there's not only carbon, soils do contribute to the global warming because of CO2, of course. Overall, soils contribute to 15% of the global warming. Most of it is due to CO2. Most comes from changes in land use and agriculture, but also N2O, and the N2O contribution comes exclusively, nearly exclusively from agriculture. The methane contribution largely comes from cultivation of rice, paddy fields. Now, how was soil being viewed in IPCC report? Again, I went to 95. It was the second report of the IPCC, and to the most recent one 2 years ago. And what is apparent is that soil was perceived as a passive pool, a passive reservoir in the 90s. And attention was focused on changes in land use and consequences in terms of greenhouse gas emissions, while in the 2010-14, there was really a change of perspective, considering that it was an active sink. And now the vision is that soil is a large-scale, relatively low-cost solution to address, to contribute to mitigation of climate change. So via management, especially management in agriculture. So the vision of IPCC has really changed. And one thing also that contributed to attract attention to soils was that it was in the 90s actually, the late Dominique Arrues and Jérôme Balédan wrote a paper together, and they calculated back-of-the-envelope calculation showing that if soils carbon stocks were increased by 4 per mil annually, this would compensate the annual efflux from fossil fuels. So it showed the quantitative importance of soil This number doesn't have to be taken more seriously than that, but it was showing that very small variations did matter. And at one meeting, the French Ministry of Agriculture, Stéphane Le Foll, heard about it, and it clicked in his mind. And this was the origin of the 4 per mil initiative, Soils for Food Security and Climate, which main objective was to raise awareness, especially at governmental level and policy level. It is, today, we can consider it is quite a trendy topic. In the HAP soil, we performed a number of stocktakes, by the way, Sophie Cornu from your lab participated and contributed a lot to the HAP soil. So one of the questions we asked to stakeholders over 23 countries was, what is the main challenge regarding soils, agricultural soils in your perspective? And maintaining and increasing soil organic carbon came first. And we repeated that 5 years after, same classification. So perceived as stakeholders as being important. And regarding scientific literature, what I did was using Web of Science, I calculated the number of course, publications rise in every domain. Everyone shows, exponential curves. Of course, it increases in every topic, on every topic. But I calculated the amount of publications searching on topics that had soil, carbon, and climate change compared to the total publication on soils. And you see, of course, it's a low proportion, but it really drastically increased. So it's a change of focus of the soil science community, especially that one working on climate change. So are soils climate smart, thanks to carbon sequestration? So I will focus. The questions that come, and for research behind these questions are, of course, the first one that may come is probably, what are the carbon storing options in management? Then comes how much, estimating the carbon sequestration potential. Then realize that some understanding is needed to select practices, to understand how long is the carbon sequestered? Is it a matter of days, years, decades, centuries? It makes a difference. So questions on understanding soil organic carbon storage and persistence, but also the goal is to mitigate climate change. So are there trade-offs? What are the trade-offs? Can we evaluate them? Can we predict them between SOC, storage, and greenhouse gas, other greenhouse gases emissions? Need to be able to robustly, accurately quantify, so developing robust measuring, measuring, reporting, and verification systems. Also, understanding, analyzing the enabling conditions for implementation on the ground, and assessing, predicting the threats to carbon sequestration due to climate change or to changes in land uses in the future. Today, I will focus on 3 of these questions. Then let's start. Understanding soil organic carbon storage and persistence. There has been, since the 90s, a real paradigm shift in our domain of research. Everyone was taught, was conceived about the humidification theory that stated that organic inputs were degraded to small molecules, and then from that big, chunky, unassimilable, uneatable molecules, humic substances, were made. So recalcitrance, chemical resistance to decomposition was the main mechanism. This was shown to be wrong, to be issued from artifacts, from methodologies. And what emerged progressively is what we name a continuum model with different processes, not only recalcitrance, but also physical protection, organo-mineral interaction, that say basically, in fact, it's much more simple, that it goes simplifying and simplifying from the biomass to small molecules, organic monomers that become CO2. And these can be more or less stabilized by different processes. And this is from Lehmann and Kleber, but Isabelle, in one of her papers, redraw it, and I find it's nicer. Since the 90s, in fact, there has been a succession of theories about soil organic matter persistence. So we started with the recalcitrants, chemical recalcitrants, saying that large complex molecules were the one persisting for longer. Then stoichiometry was what really became important and fashionable. Then physical protection, that organic matter protected within aggregates was not usable, not accessible, not usable by microorganisms. Then that organic matter adsorbed to minerals was not usable for minerals, that is association with minerals. Then a more recent focus on microbial transformation and on energetic aspects, well, microbial physiology. So here I'll give a few examples of results. I took one easy one first, physical protection of the organic matter. Where our perceptions in this area have changed is that it was all about aggregates in the 18th, 19th, and now it is a matter of microbial habitats. And I will show you one result from our group where we explored the microbial biogeography at the scale of pores. So we added C13 labeled pyruvate, easily usable substrate, to pores of different sizes based on Laplace law, and incubated the samples in 6 contrasted soils. And we found that when the substrate was initially located in the larger pores, 30 to 100 micrometer, they were decomposed faster, at least in 4 of the 6 soils. And actually, we also found that the efficiency of microbes in these large pores that were favorable habitats was much less than those in small pores where microbes were where the substrate was decomposed slower. So this shows that there's contrasted microbial habitats that can shape carbon decomposition. And the research area now is evolving towards modeling with models that represent, at the scale of microbes, the exact architecture of soils, the location of microbes, of organic matter, all the fluxes of carbon, nitrogen, water, and using heavily micro-CT tomography. So very mechanistic, deterministic models. The challenge for the future is to link those models to 1D, larger scale models that are the ones being used in the field. So that was first physical protection, then organo-mineral interactions. The vision in the 90s was of organic matter nicely adsorbing to clay mineral surfaces. Sometimes in some papers, there were calculations of how much it represents in terms of monolayer. There was even a theory that came out of that at one stage, if all mineral particles, if all clay surfaces were covered with organic matter, there should be a saturation, so no more possibility to protect. And this adsorbed organic matter is less decomposable by microorganisms. Changes since then, in my perception, have been to enlarge the processes, that is involving considering co-precipitation as well, and also widening the type of minerals, not only clay minerals. And here one example is the ongoing studies on nanocliques, nano-sized co-precipitates of inorganic polymers with organics. So these remain to be quantified in many environments. Well, there's a lot to do on that. But for me, there was in this area of the literature, there was also one change that was considering first that once adsorbed, okay, static, nothing happened. And now it's much more the perception of scientists and the papers really consider dynamics. That is destruction of these organo-mineral interactions, either because of weathering or because of decomposition of the organic components. So much more dynamic perspective. Now, I'm still following, in fact, the order of the graph I showed you from the Derrien paper on the successive theories on organic matter stabilization. In the, you see the 2010 and so, the idea that was really exciting most scientists in the area is organic matter, in fact, soil organic matter, in fact, only microbial? So with here, what I put is a scheme from Liang et al. That shows, of course, microbial growth that uses the organic matter. There's some recycling. But when they die, they are necromass. And this necromass is thought to be stabilized by adsorption to minerals or by entrapment into small pores within the soil. This necromass or the microbial metabolites, all the molecules, EPS, for example, that microbes release in the soil. And what was, there has been one difficulty we have in the area is that we only have one biomarker for necromass, amino sugars. So when you have only one biomarker, well, I tend to be a bit cautious, but the result that really is accepted by most of the community is that nearly 1/2 of, and this is this graph, 1/2 of the soil organic carbon in different ecosystems would be, in fact, microbial necromass. So this is prompting, if everything goes, in the end, is stabilized because it goes through microbes, then it sheds the light on the microbial metabolism, on physiology, and a number now ongoing studies in the area, what is most active, are studying the carbon use efficiency, that is how microbes allocate the carbon they assimilate to building their cells or to producing energy, respiring. Because the cells they build, it remains in the soil, it will contribute eventually to the stabilized carbon. And also on energetic controls of that. What is the energy balance of microbes when using different substrates? So here we are now. I gave you example for 4 of these theories on organic matter persistent. What we can say is that, in fact, all processes coexist. They all coexist. And likely in all soils, they all coexist. Yet, the questions are, what is the relative importance of these processes? Is it the same in different pedoclimatic conditions? Is it the same in different land uses? Is it affected? Is the relative importance affected by management options, management of soils? So this is one of the standing questions. And also, what is this century scale stable soil organic matter? Could we isolate it? Could we measure it? We need to quantify it because it's so important in terms of long-term mitigation. And here, yes, one example to try to link agricultural practices to stabilization processes. So I put different stabilization processes. And for example, you see for physical protection, what favors is incorporation of organic matter in small pores, having anoxic pores, having low pore connectivity so that microbes cannot access, good aggregation, aggregate stability, and seldom perturbation of the soil structure because it will ensure that a protective microbial habitat will remain long in time. Same for microbial processes. What would be interesting would have microbes with high carbon use efficiency. Behind that, well, it was shown that rhizome deposition is extremely important and high quality decomposable leaders, and of course, microbial assimilation. So it's possible to link these processes, rhizome deposition or facts, high quality decomposable leaders, and processes again, microbial assimilation to the different processes, and to try to link agricultural practices. So I told you I would not speak about agricultural practices. They will be mentioned twice. For example, tillage, you can influence aggregation, perturbation of the soil structure, existence of anoxic hotspots, etc. So, but we have no consistent, solid framework to build upon yet. Well, I'd say it's work in progress. And regarding management options, I wanted just to mention that for me, well, it's my perception, so colleagues here, soil scientists may disagree with it, that most innovative, promising management options, at least that need research to understand how and how much, are all practices that influence the quantity and the quality of below-ground inputs, that is rhizome deposits, root architecture, and all practices, land use, etc., that influence diversity of the plant cover, diversity of the soil inhabitants. And soils are Yes, and this is to be analyzed in different ecosystems. So this morning it was said that soil is a 1D system. Soil is a 3D system, extremely heterogeneous across space. Now, estimating carbon sequestration potential, how much? First, I would like to present you some intrinsic limits to increasing carbon stocks in soils. This is a theoretical graph with, you see the reference, management option. Stocks are slowly decreasing. That's most representative of croplands worldwide. Slow decrease. Now, and yes, in x-axis, it's the time. Look at the time scale. Priority, if you change management, for example, return a permanent grassland, there's a drastic loss in organic carbon stocks. So the priority is to protect the existing stocks. Now, if you implement certain practices, cover crops, agroforestry, stocks will increase. There will be an additional carbon storage compared to the baseline. But these stocks plateau at some stage. A new equilibrium is reached. And they are management dependent. So it's slow. Look at the timeline. It's limited, and it's management dependent. And if the management is changed, it is reversible. So this is a real challenge. The time scale and the reversibility are real challenges in terms of policies, adequate policies to support farmers, land users, to promote carbon sequestration in soils. And there's a need to avoid leakage, that the storage you do on one site is not at the expense of the storage at another site. For example, applying manure all in one field, except that spreading it or applying it in another field. And this, I introduced additional carbon storage in soils compared to the baseline. What IPCC named carbon sequestration is a net uptake of CO2 from the atmosphere. In the AJP soil, we did a survey of the use of the term carbon sequestration in the 100 most recent papers at the time of our analysis in this field. We found first that in 42 papers, it was a buzzword. There was nothing about carbon sequestration. And it led us to develop these. For example, this looks like the graph I just showed you. Business as usual, implementing, for example, cover crops, carbon stocks increase, plateau. There's an increase in carbon stocks, there's a net carbon sequestration, net uptake of CO2 from the atmosphere. Now, if the business as usual is like that, the carbon sequestration, the net uptake of CO2 from the atmosphere compared to time zero is less than the additional carbon stored. And in some cases, you can have additional carbon sequestration, additional carbon storage, but no net uptake of CO2 from the atmosphere. And it is very important to quantify organic carbon stocks both at time zero and in the business as usual scenario. And misunderstanding, not understanding this, the importance of the baseline under business as usual may really lead to disappointment, especially from land managers and from policymakers. You have implemented a practice that is known that actually does store any more carbon, but no changes in CO2 uptake. How much? So I wanted to show you one example, and in the end, well, it's easy for me, but it's also that I think it's really a great study. I will give you a French example of a study that was led by Sylvain Pellerin and Laure Bamière at INRAE with a collective whole group of experts. So what they did, is to use data from the French soil database, Climate French database, agricultural plots, graphical register to define spatial units on which current cropping practices could be informed by other data. And this allowed to model this baseline using soil carbon dynamics models in cropland sticks, in grassland passive. And then modeling allowed to model in a second time the effect of implementing storing practice. And we worked only on practices that had been established in the literature as being very good candidates. Also, the surface on which a given practice could be implemented, that is, it's not yet implemented, and biophysical conditions are there, was estimated. Now, multiplying the two gives the additional soil organic carbon storage. So here are the results for mainland France per hectare. So you see that the management options that have been considered have very different efficiency in terms of annual carbon storage as averaged over 30 years, but per year, in tons of carbon per hectare and per year. And then multiplying those numbers by the surface area where it was possible to additionally implement those management options gave this. Different classification, different ordering of the management options. Summing up all practices, all management options that could be run together, you can have cover crops and agroforestry together, for example, gave rise to, a number of millions of CO2 equivalent. What is meaningful as a number is that these represent 6.5% of total French greenhouse gas emissions. And this equals 41% of French agricultural emissions. So it will not save France, but it's a contribution that deserves to be used, to be implemented, to be mobilized. Now, what was very original in this work compared to what is usually found in the literature is that colleagues also estimated the economic potential, calculating benefits and costs for implementing each management option and setting a ceiling. Okay, I only want to implement what costs less than 55 euro per ton of CO2 equivalent that is mitigated, or 25, or 0. And you see that the additional carbon storage potential considerably decreases. So it's very important not to have only technical estimates, first part I showed, but also economic estimates. And in the AJP soil, we wanted to, of course, to continue and spread this type of exercise. And first, we evaluated what was done, what was there. We did a stock take. And what we found is that, only 14 countries had made a national estimate of the carbon storing potential of their agricultural soils. I will not comment, but see that each color corresponds to a different management option, a different agricultural practice. You see that some countries considered only one management option, biochar in Norway, no-till in, in Spain, for example, while other countries considered different management options. And there was absolutely no homogeneity of the methods. Then it's really important to harmonize the methods, and we launched a project to do that. So colleagues from 23 countries got together and choose a methodology. So they use a tier 2 methodology, so not modeling, but calculating from long-term experiments the rate of carbon increase, so carbon increase with time for a given management option. And they estimated the potential area of implementation based in particular on biophysical limits. Is the good season long enough, for example? Is our soils deep enough, etc.? So estimated areas of implementation and then multiplied. And of course, it's a different order. And yes, I showed you an example to tell you that it has been done. Now, doing it by modeling is still not finished, but I wanted to raise your attention on one point. Look at biochar. What they first did was to calculate how much you can add of biochar to soils without compromising soil functioning. And they get to this number, huge carbon sequestration potential. But they rapidly found that this corresponded to more than 40,000 years of the current production of biochar in Europe. So it's not technically feasible. And the second bar, I put available biomass, is using all pruning, really using very widely biomass to do biochar. So even defining what is a technical estimate is a matter of debate, and we are still debating, I'm still discussing with them. Same for woody features, they consider different estimates. Okay, and again, fair contributions will not save Europe, but good contributions. Now, at the global scale, then I went to the last IPCC report, and what is said is that cropland, what is written is that cropland and grassland management of soil carbon can lead, in average, to 4.1 gigatons of CO2 equivalent per year with a huge uncertainty, and they really insist in the report on the uncertainty. And they advise to use rather the range than the average value. But what I did was to calculate in carbon, gigatons of carbon, to allow you to compare from, so 1.1, and I gave you the global carbon cycle, saying that the net flux of carbon from our planet to the atmosphere is 5.2. So again, the wider the surface area, the scale you consider, the larger the uncertainties, and the less databases are available. But still, we always find at different scales that it's not solving the problem, but it's a fair contribution that deserves to be mobilized. And in fact, different carbon storage potentials can be estimated. Biophysical potential, it's the most you can achieve in a given ecosystem. Technical potential is what you can practically do, what I showed you for France, for Europe, and what was calculated for the world. Economic potential is what you can do for a given cost. But there's also what is feasible given the know-how of farmers, given the regulations, given the land tenure, etc. And this, we have no methodology, no set methodology to estimate it. And that's actually the on-the-ground valid number, but very few numbers except in case studies. And again, no established methodology. So on this section, I would like to say that, yes, we need for an agreed upon methodology to avoid disappointments, misunderstanding, for explicit and harmonized methodologies, and for estimates of this achievable potential. Now let's go to MRV, Measuring, Reporting, and Verification Systems. I will be shorter. What I wanted to tell you is that, so there's a lot of work right now, a lot of research on that right now, lots of engineering on that. And it is going towards a system where you do not only rely on soils, on measuring carbon stocks. Why not simply measuring the evolution of, over time of carbon stocks in soils? Because the variation is small over large stocks, so sensitivity. Because the changes are slow, you need at least 5 years to go back on the field and remeasure. Otherwise, you will not be able to distinguish anything. And there's a huge spatial variability. Soils are very spatially variable. And it has a cost, especially the labor. Can we use remote sensing? Remote sensing is precious, but so far are still very much problems with accuracy and certainty, not bias, but yes, artifacts. And it measures organic carbon contents at the very surface, not stocks over 30 centimeters. And can we use only modeling? Well, yes, but you have to calibrate and to validate your models. So the scientific community is now going toward what we call a hybrid MRV system for soil carbon, where, let's take a farm. Of course, at the center, there is a soil crop model that will estimate the evolution of organic carbon stocks over time. A farmer wants to be paid for additional carbon storage, wants to implement cover crops, but could consider agroforestry. Okay, so use the modeling. But the models have to be fed with farm data on activity. With remote sensing is very useful, again, for activity data, for biomass estimates, to feed the models, and for continuity, spatial variability of the soil properties. Not for soil carbon, but for that. Data sources on climate, soil, land cover, history of land cover, and soil sampling is needed at the very start, and sometime, maybe not every 5 years, maybe not every 10 years, but sometimes for ground truthing. And then benchmark sites to test the practices, measure the fluxes, and model calibration and validation. So it's really, we're going towards really hybrid systems that involve scientists from different disciplines. Yes, this is for MRV. And I had 2 comments about this after this presentation of what can be an MRV system nowadays. It's about models. So in this area, there's a strong reliance on models. Now, Julia Lenoé, well, under the supervision of Pierre Barré, did, with a whole group of co-authors, an analysis of models, whole carbon models, 92 models. And she analyzed how were calibrated and validated the model. You can have no prediction, you can have no independent evaluation, you can have an independent evaluation that can be one point in time, space for time, quite frequent, or diachronic evolution, a long-term experiment. This is the most solid. Now, what she found is, look at the numbers, is that very few models have been actually, or are actually being validated using independent diachronic measurements, data, only 20%. So we really need to progress in this area, and I didn't put it, that's really need to progress in this area. And for that, for independent diachronic validation, we need long-term observatories. We need long-term experiments, benchmark sites. And again, in the AJP soil, we built a database of metadata of long-term experiments, so more than 200 long-term experiments, and now have a description of the management options. And Bonares in Germany is hosting this database, so you can consult it, use it. And for example, it is being used, and even it will go much further with a fair carbon pair project that is assembling data on long-term experiments, climatic data, to have toolboxes for modelers, to compare models, to validate, to test their models. So this is what I, well, in a scattered way described. Now I will conclude. So are soils climate smart? I think yes, they can be. They can be. There's a large technical potential for sequestering carbon and mitigating greenhouse gas emissions at relatively low cost. So I showed you the cost, how they were limiting the implementation of practices. But compared to deep soil, to deep carbon storage, for example, it's much, much cheaper. They can be when properly managed. They can be when you account for trade-offs, and recent studies show that trade-offs limit the mitigation potential, well, N2 emissions limit the mitigation potential when you have additional carbon storage, but generally do not overcome it, do not annihilate it. And when being aware of intrinsic limit, it's a temporary solution. When you reach a plateau, no more additional carbon storage. So it might help us until we find other solutions at other scales. And they're also climate smart because of the multiple benefits of sustainable management and of soils rich in organic matter. Oh, it doesn't work. Okay, so yes, it works. Yes, I had some general comments. I tried to, the animations do not work. Regarding the context, we're in a context where there's increasing accounting, increasing incorporation of carbon sequestration in policies. Of course, the Paris Agreement, the EU climate law, several national climate laws and plans, the EU regulation for carbon removals and carbon farming that has been voted. there's an increasing relevance of carbon sequestration in soils to the economical world. It's kind of the far west, many companies developing in the area of carbon farming. So it's a trendy topic. And the good side is that many scientists getting interested, funds being available, but the dark sides for me are using carbon sequestration as a buzzword, that the terminology is really flawed. Many opinion papers, too much, I think, compared to the data we provide, and very often an overgeneralization, because you find something somewhere, you consider it's, the title of your paper says it's true worldwide, which is wrong. So needs and challenges are to go from, of course, we do need better understanding of the processes, and we do need to be able to quantify carbon that has different residence times in soil. And we need to go from fine-scale mechanistic understanding to robust and generalizable and understandable knowledge that is understandable by managers, by policymakers. We need harmonized methodologies and frameworks, for example, how to account for pedoclimatic conditions. This is really missing. We need collective systematic assessments. IPCC is doing it, but I think in soil science and in the area of soil carbon and soil climate change, there's a need for more in-depth, more precise collective assessments, and of course, to have not only the biophysical research I have been describing, but also socioeconomic research. And on that, well, it doesn't work, but I would like to thank you for your attention. And I hope you have questions.
Much, Claire. Are there questions? No questions? I have one question. Claire, you showed us that cover crop is very efficient in France, but in Europe it's completely the opposite. How do you explain this difference?
It's, for me, it's kind of a methodological bias, and there are active discussions with the leaders of the project that they based their estimations only on long-term experiments in Europe, for which they could access completely the data. And so they did not consider literature from similar pedoclimatic zones in other continents. And I think it's a pity, because in China, in America, there are many huge surface areas of agriculture where basically it's the same pedoclimatic conditions as in Europe.
Okay, thank you.
Yes, thank you, Claire, for the very nice talk. It's a very naive question. I'm not
go ahead.
A soil scientist specialist at all, but somehow when we store carbon in organic matter, we also store nutrients.
Yes.
So I always struggle figuring out how we keep rich soil with nutrients available for the production, and at the same time, we store carbon in a stable
Thank
system.
you. That's a question practitioners always have. So thanks a lot. Use the organic matter or hoard it, store it. Well, in fact, it's possible to combine the two. If you increase the inputs, in terms of biomass inputs, for example, having cover crops in addition to your crop, or adding manure, adding composts, then you can both, there's enough, so you can both have part of it that is more labile components or not protected, that will mineralize and then provide nitrogen, phosphorus, sulfur, and part of it that will be long-term stabilized. But, well, it's like our bank account. If we want to be able to spend daily and to save money, we need to earn more. Thanks for the question.
But I have a question about the depth that is considered when dealing with soils, because you say we are lacking of data, but most of the data are about the 10 or 30 centimeters top, whereas soils can be several meters of depth. And when we deal with steady-state mass balance or steady-state cycle, it's quite important. So what do you think of...
Well, what is generally accepted, at least, and it comes from IPCC as well, is considered that the 0 to 30 centimeter is the reference layer. That is the minimum you must have. But yes, in fact, we are ignoring this way nearly the same amount of carbon that is stored deeper, carbon that is stored, and Jérôme Balédan worked a lot on that is stored with much higher residence times, so that's really important in terms of mitigation of climate change, and probably in terms of properties of the upper soil also, but this is not studied. And so, yes, I think it's because it's kind of difficult to sample, it's labor intensive. And what is, I think, is a pity is that I saw it in the AJP soil that it's quite a frequent habit when working on practices that essentially affect the upper 10 centimeter, just sample the 10 centimeter. So no, we have at least to stick to 30 centimeter depth, and if possible, more. And by the way, the estimate of 1,700 gigatons of carbon, it's the upper meter. It's not deeper.
Okay, another question there?
Yeah, thank you for a great talk. You mentioned that the soil community is still debating if a significant part of the organic matter in soil is made of dead microbes or not.
Is made of?
Dead microbes?
Yes.
And it's such a dramatic hypothesis that it's kind of weird that you can't quantify it properly, even visualize it. And
okay. Oh, thanks. Well, visualize it. It's not easy because it's microscopy. Soils are opaque. And well, the main difficulty is that microbes are made of the same molecules as plants: sugars, proteins, lipids. So you have no, if you do imaging, you have no probes that are specific to microbes. And so far, the only probe that has been found to quantify microbial necromass is amino sugars.
And there is no carbon isotopic fractionation during the assimilation? No isotopic fractionation of the carbon through the assimilation? Or?
That would make the microbial necromass, yes, we can expect it to be slightly more enriched in C13 compared to what they used, but I don't think it's enough, and you would need to separate them physically for that. So, no, and yeah, so this estimates that half of the soil carbon is dead microbes. Maybe it's true, but it's a pity that we have only one methodology.
Could you comment a little bit about your two first lines? What are the efforts to have a real implementation in agriculture? Because you commented mainly on the scientific knowledge about carbon sequestration.
Well, efforts to have a real implementation in agriculture, well, most agroecological management options, agroecological cropping systems, are systems that store additional carbon. So I would say normally the motivation of farmers is not to store carbon. It's not they want to produce more. They want to produce, even that producing more, they want stable production over time, over years. But yes, many of them are, in fact, want to implement conservation agriculture, want to implement organic agriculture, want to implement cover crops, flowered bands, because of general effects on the ecosystem and on soils and on their production. So usually the motivation is not carbon storage, and we cannot ask them to be motivated by that. But now an economic sector that is really developing fast, what I named the New Far West, is carbon farming, that is paying farmers for additional carbon storage. And there's a number of companies that do that, so it's voluntary contribution, and it's, well, yeah, it's tempting for them, it's tempting for farmers because some pay quite well. And I remember discussing with one farmer that has been under conservation agriculture. He has been one of the early adopters. Well, they're convinced, and he told me, yeah, I'm being paid by this company. Come on, they don't ask for anything, and they pay me, I don't remember how much per hectare. Why should not I do it? He's right, actually. And also, so this is, and this uptake of carbon in soils, well, the problem is often it's not verified. In that case of this farm, they did not verify anything. Scandal. Is that companies may use these to compensate for their own emissions. So that's offsetting. And now there are also companies, especially food companies, that want to compensate their emissions in certain sectors by rewarding farmers for the additional carbon stored. So they want to act on their own food chain, on their own value chain. So I don't know if I answered to you. But yes, we can have a look at the Common Agricultural Policy. In France, it's a pity. It's really a pity. We're going backwards.
Thank you.